Hi guys, welcome to your second Chapter 7 video. This is more on Introduction to Scatterplots, and this time we're going to get a little bit mathematical with our analysis of these scatterplots. Keys with scatterplots to remember, they always have two quantitative variables, one on each axis. They're going to look a lot like coordinate pairs you've worked with in the coordinate plane in the past, but remember, even though you've got an explanatory variable on the horizontal axis, response variable on the vertical axis, these do not indicate cause and effect. Unless you've got some crazy things going on, just because you've got one variable that helps to explain what you see in the vertical response, we are not equating the association between the variables with causation from the explanatory variable to the response variable. All right, so this concept today is all on the correlation coefficient. Correlation coefficient is a statistic that summarizes the strength and direction of the data in a scatter plot, but it's calculated assuming that our form is linear. That's important. So that means you can actually find a correlation coefficient for any scatter plot, but it doesn't necessarily make it an appropriate statistic. Just like if you had heavily skewed histograms, the mean may not have been appropriate. You could still find it, but that doesn't mean that it's appropriate given that particular context. Here, the correlation coefficient makes most sense to use when you've got a linear form in the data. Okay, so two things about this correlation coefficient. The two properties of it are first the values. Oh, well, we're going to get to the characteristics in just a second. Correlation coefficient takes values in the interval from -1 to +1. And on the extremes, you could have a correlation coefficient of -1 or of +1, or anything in between, including 0. The correlation coefficient can be understood by its two characteristics, sign and magnitude. So, regarding sign here, this third paragraph is all about sign. Any correlation coefficient that is positive indicates that the direction of the data is positive. Any correlation coefficient that is negative indicates that the direction of the data is negative. Okay, that's easy enough. So if you have an R value, if you look down below of this -0.8, the data tends to have a negative direction. R values, the next three, R being correlation coefficient here. That's the variable we'll use to represent the correlation coefficient, R. Any R value of 0.2, 0.006, or 1 indicates that the data is increasing from left to right. All right, finally, the magnitude of which is the absolute value of the correlation coefficient, gives the strength of the association, the strength of the linear association, because the correlation coefficient assumes you've got a linear form. Correlation coefficient that has magnitude 0.9 has a strong, and I really should put in there, a strong linear association, while a correlation coefficient with magnitude 0.2 has a much weaker linear association. So magnitude of R is equal to the absolute value of R, the absolute value of the correlation coefficient. So, a few things there. It goes between -1 and 1. The sign indicates the direction the data is moving in the scatter plot, and the magnitude tells us the strength of the association of the data in our scatter plot. Okay, so here on this slide you've got a few examples of different scatter plots, 6 in all, with axes don't really matter. The goal is just to look at how, given different groupings of data in a scatter plot, you can have different correlation coefficient values. You can have different R's. For the first one here, obviously top left, you've got an R value. Well, let's actually look at it first row. The first row, R equals 0.7, then R equals 0.3, then R equals 0. All those correlation coefficients are non-negative, which you can see makes sense given that none of them move in a negative direction. The first two have positive R values, hence they are moving up from left to right. And in the second row, we're seeing the opposite. We're seeing, that should be R equals -0.3. In the second row, we're seeing R values where the data is moving down from left to right. Hence, we have at least non-positive correlation coefficients, we've got R value of negative 0.7, R value of negative 0.3, and then the last column here, that third column with the two scatter plots that have R equals 0, we're seeing that because it's basically telling us that there is the strength of the association, the strength of the linear association, hence the line drawn through it, is as weak as you can get. There's really no linear trend in the data. Also, because the correlation coefficient is 0, it doesn't tend to be increasing, it doesn't tend to be decreasing. On the other hand, first column, if you look at these 0.7s and negative 0.7s, you're seeing the magnitude of R for both of the scatter plots in the first column would be 0.7. If the magnitude of R is just the absolute value of R, you've got a magnitude of 0.7. Hence, compared to the second column, our association is stronger than in the second column where you have magnitudes for these correlation coefficients of 0.3. There's more scattering in the data from the line that approximates the trend that the data has in the scatter plot. All right, so again, you're seeing direction you can get from the sign of the correlation coefficient, and the magnitude gives you some sense as to the strength of the linear association the scatter plot takes on. All right, what we're going to look at next, I struggle with whether or not I want to teach this each year, and I think it has value. I think it's confusing. The next few slides will be confusing, but at the same time, I have tried to establish scatter plots that will make this as clear-cut as possible. Listen well, take good notes, and you will do just fine. So, okay, the correlation coefficient is calculated using the following formula. R, the correlation coefficient, is equal to the sum of the, for every point in the scatter plot, you multiply, check out this numerator right here, for every point in the scatter plot, you multiply the number of standard deviations from X bar and the number of standard deviations from Y bar. From the mean of X and the mean of Y, divide through by n minus 1 is approximately n, the number of coordinate pairs, the number of points that you see in your scatter plot. Okay, so in the past, we have, well, in the past, last time I saw you guys, we saw these scatter plots, and we hadn't talked about characterizing the data like we did in the numerator right here, which I will recircle in blue. We hadn't talked about characterizing scatter plots according to z-scores, according to standard deviations. We're going to look at this scatter plot we're seeing on this slide recharacterized on the next slide. So this scatter plot, let's start with what this is. This scatter plot is showing us the trend for 12 students, the trend between, the association between their high school GPA and the average number of hours spent studying per weeknight. So we see sort of a logarithmic trend. You do get payoffs as you spend more hours every night studying, but there seems to be it's diminishing returns. For every hour spent, you don't get an extra like 0.5 in your GPA. Initially, we've got that strong increase. Then it sort of levels out a little bit, and you don't see the same sort of returns in your GPA for every additional minute or hour spent studying. Okay, so these data points here, yeah, it's got a logarithmic trend. Not really what I want to focus on for now. These data points here, remember, let me circle this guy right here. That has got an X value of average hours spent studying per weeknight. I'll leave that out for the sake of being concise. And then your Y value would be GPA, okay? All right, so that's going to be true for all of these coordinate pairs. There's some number of hours spent studying versus GPA for each one of these guys. All right. Well, if we go on to the next slide, we're going to look at the same scatter plot. Notice I tried to keep this as identical as possible. You've got the exact same data. You've got 12 points corresponding to the 12 students who have some number of hours spent studying and some GPA. So it's the same 12 students. And this time, your x-axis is not average hours spent studying. Your y-axis is not GPA, but instead you've got an x-axis that is the z-scores for that x variable, the z-scores for number of hours spent studying. That is to say, for each one of these little points, let's check out this guy right here, we've got the standard deviations from x, x bar, from the mean of x, number of standard deviations from the mean of x, versus the number of standard deviations from the mean of y. Okay, so check out what I've thrown on this scatter plot. I have two dashed lines here representing the mean of x, the mean number of hours spent studying, and the mean of y, the z sub y equal to 0, the mean GPA of these 12 students. Okay. So this correlation coefficient says, okay, getting back to this numerator right here, it says, let's look at every point on the scatter plot, and for each of these points, we're going to multiply the number of standard deviations from x bar, let me add those bars in, times the number of standard deviations from y bar, the mean of y. Because remember, we've got, with the scatter plot, we've got two quantitative variables. Hence, you've got a mean for the x variable, and you've got a mean for the y variable. Again, represented by these dashed lines. So how does this work? So we're looking at, let's check out this point right here. Its z-score sub x bar here would be this distance, okay? The mean from the distance in standard deviations from the mean of all our x values here. And its z sub y bar would be the number of standard deviations from the mean of y. So you've got standard deviations from x bar, you've got standard deviations from y bar, and you're multiplying those two together. When you multiply those two distances, standard deviations from the mean of x and standard deviations from the mean of y, you get this rectangle right here, which, because the z-score for x of this guy and because the z-score for y of this guy are both positive in this case, we are to the right of the mean of x and we are above the mean of y, hence we have a net positive effect. That would give the correlation coefficient for this scatter plot a positive trend. Okay? Same thing with this guy right over here. Okay? We've again recharacterized this data according to the standard deviation. So you've got right here, you've got a negative z-score from x bar for that, and you've got a negative z-score from y bar, from the mean of y, okay? But when you multiply two negatives together, obviously you get a positive. So here too, you have a positive trend going on from that point to lean, it makes the correlation coefficient more positive. So all of these blue points right here that I'm circling give a positive trend to the correlation coefficient. They make it, they force it to be closer to a positive 1, the correlation coefficient. Let me back up now and erase one thing, and we'll look at a data value in the upper left. Let's erase this and this. Okay, so let's check out this guy, for instance. It, on the other hand, has its z-score for the x variable here. That is negative. We are below, we have negative standard deviations from the mean of x. So this is a negative z-score, okay? And then this guy is positive, positive z sub y bar, all right? Net effect of all this is that when you multiply this negative and positive together, you have a negative trend going on from this point to the correlation coefficient. So this correlation coefficient, the way you can conceptualize this is that this correlation coefficient right here is looking at all of these, I don't know what to call them other than standard deviation boxes. I've never heard a name for these things. I've never found a name for these things. I call them standard deviation boxes, and this is how I conceptualize it. You're just looking at from where my mean of y and from where my mean of x hit, right in the middle, what trend do these points force? Everything in blue has a net positive effect here. Same with these guys, because everything in blue lower left has a negative standard deviation from x bar and a negative standard deviation from y bar. Hence, you get positive trends in here. In red, however, you've got these 3 points which are forcing the correlation coefficient to be a little bit more negative. You've got this heavy blue trend which forces the correlation coefficient to be positive, to be closer to 1, but then you've got this negative trend because all of the z-scores for x are negative here for all of those 3 circled guys, but their z-scores for y are all positive. Okay, so that's the confusing bit. Let's check out. We're going to check out a few more examples here. Let's say that. Let me pause here real quick to look at one other thing. Okay, so yeah, we've got this. Let's check out what happens when our data is perfectly linear. So we've got some new scatter plot. No, the data is not the same as what we'd seen before with average hours spent studying per week 9 and GPA. We've got these 7 points all in a line. You've got the mean of x represented by this vertical dashed line. You've got the mean of y represented by this horizontal dashed line. And those are in z-scores, so you've got 0 and 0 for each, because they are the mean. They are 0 standard deviations from the mean. So here too, again, the data is being characterized not as hours spent studying, not as GPA, but each coordinate pair now is just like before. The z-scores, the number of z-scores from x bar, and the number of z-scores from y bar. Okay? Well, check this out. You've got a positive z-score here for x, and you've got a positive z-score here for y. Hence, the net effect of this guy, when I multiply them together, remembering that your correlation coefficient takes all your points, multiplies their z-scores from x bar, z-scores from y bar, divides through by basically the number of points you've got. Well, the net effect from this first point that we're highlighting would be positive, because the z-scores are both positive. Same for this guy and this guy. Well, here bottom left, same deal. The net effect is also going to be positive, because now for these 4 points bottom left, they have negative z-scores from the mean of 0 and x, and they have negative z-scores from the mean of 0 and y. So these all contribute to a positive trend as well. You have nothing but positive contributions to this correlation coefficient. Hence, the correlation coefficient in this case would be equal to just 1. Okay? You've got as strong a linear trend as you could possibly have. There are no negative, so I'm going to call them counterweights, no negative influences upon this correlation coefficient like those 5 red dots would indicate for us. Hence, we get a very strong correlation coefficient of 1, meaning that the data is going up from left to right, and it is perfectly linear in this case. All right. On the other hand, if you've got data that is just kind of nebulous, that it has no association here, your correlation coefficient is going to be 0. R will be 0 in this case because basically, in layman's terms, for every point that has this positive contribution of positive z-scores of x, positive z-scores of y, I need bars over those, for every one of these guys that creates a positive influence upon our correlation coefficient, you have a counterweight of some point here in red that has, it will have in this case, a negative z-score from x bar, but a positive from y bar, indicating that the overall influence from this one red point upon our correlation coefficient would be negative. And when you've got data that is like this, that is just sort of all over the place, the positives and negatives will, in effect, cancel each other out. It's not quite as simple as just addition in that way, but they do cancel each other out when it gets to the correlation coefficient calculation. And you have correlation coefficient of 0. There is no linear association in this scatter plot. Okay, so one thing to highlight as I've been going through this, I could be making a lot more of these standard deviation boxes that I'm putting either positive signs or negative signs within. There are just too many for me to highlight, but hopefully the color coding has helped here. Color coding should indicate anything in red has a negative influence upon the correlation coefficient. Anything in blue has a positive influence upon the correlation coefficient. And that influences whether or not your correlation comes out to be 1, -1, 0, or something in between those three numbers. All right. So now that I've sufficiently confused you, let's go ahead and check out how to use our calculators to calculate a correlation coefficient with the same data we looked at from the Chapter 7, Part 1 notes. So let me pull up Wabbit real quick. And I think I've got the data preloaded, drop in duration. Oh yeah, I think I'm good to go. Okay. Edit, yeah, it's all there. Okay, so this is the same data that we saw last time with drop distance in feet, the duration in seconds for roller coasters. Let's check out the scatter plot one more time. Wait, I don't want the first one on. I had the second one on. Yeah, I had the second one on. Scatter plot's chosen. Drop. We're using, again, context is important. I didn't give you guys a context for this. So let's assume that we're trying to come up with how long in seconds these coasters will last based upon the drop feet and distance of their biggest drop. All right, so now that everything's entered, we've chosen the scatter plot. X and Y look good. We've chosen the mark that we want to use in our graph to represent a point on this graph. Let's zoom and then zoom stat and check out what we got. Well, we're seeing, let's think about what the correlation coefficient should be here. Remember, it's calculated based upon all these points and their z-scores from the mean of x times the z-scores from the mean of y. You add up all those different standard deviation boxes like I was showing you in the notes. Well, we do see kind of a positive trend as we're going from left to right, but the data is not particularly linear. We've got a lot of shifting around here. The association's weak, but we do see a positive trend. So I would expect to see a correlation coefficient of maybe, I don't know, maybe 0.3, maybe 0.4, based upon the fact that the association's weak, but we do see positive. Okay, so let's see if we can confirm that. We're just taking a stab in the dark right now. We're going to go stat, calc, and now we're not going to use one var stats because obviously scatter plots have two variables. We're going to go to linreg. We'll use this a lot next chapter for linear regression. We're going to choose linreg, and then you choose your lists. Now again, because we're working with the scatter plot here and we have two variables of information, we need to choose two of them. So we're going to go second stat to choose this blue list option. And the first variable should be your x variable, your explanatory variable rather. So we're going to choose drop. Then we will put in our comma, and we'll go second stat for the list options again, and we'll choose duration, and we will enter that. And oh, this calculator needs to be set up. This is actually a good thing to see. If this is all that you get, this is not all the information the calculator can give you. We're going to backtrack one step. This is a one-time thing you're going to do in your calculator. We're going to go to second 0, which gives us the catalog. These are all the features that the calculator has for you, all the functions in the calculator. There are a lot. It's kind of cool to look through them. The alpha lock is set up, meaning that if I want to go to diagnostic, because AlphaLock's set up, anything in green is what's going to be used for these buttons. If I want diagnostic, and I can actually hit the X inverse button, and it'll take me to all the D's, so it allows me to search by first letter. I'm going to hit diagnostic on. This again is a one-time thing. Once you set it up on your calculator, you shouldn't have to repeat this. Hit enter. Now that's done. Now I'm going to go back to stat, back to the calc menu. I'll go down to linreg, and once again I'm going to choose my lists. We've got drop and feet was X, comma duration is Y, and let's hit enter there. Now we got more information. It gave us R squared, which has no meaning to you guys yet. That will have meaning either in Chapter 8 or Chapter 9, I can't remember which. And then here's the R value. I guessed about 0.3. I said maybe as high as 0.4. It's 0.35. Okay. All right, so we got our R value, correlation coefficient for this data that we've already checked out on the graph, the calculator scatter plot equal to our 0.35 in this case. Cool. Cool, cool. So that's one more calculator function that we've got. It's less calculation by hand because honestly, you don't want to have to use that correlation coefficient calculation yourself. That is big and cumbersome. All right. Okay, moving back here, we got the correlation coefficient. There are some important properties of the correlation coefficient that need to be mentioned. And this is going to wrap up the notes. You guys have been very patient. You've done a great job. Let me check time. 26:30. Oh, wow. I'm surprised. Feels like it's been longer. Correlation coefficient treats x and y symmetrically. It does not matter which variable is on each axis. The correlation coefficient will be the same. Why? Well, if all I do is flip my z-scores for y being on the horizontal axis and the z-scores for x being on the vertical axis, it won't change the fact that over here I'm still just multiplying those z-scores together. So it doesn't really matter which one goes explanatory, which one goes response. The calculation is the exact same. It won't change the number of standard deviations that I am from the y variable if I put it on the explanatory axis. That does not change anything with regard to this correlation coefficient. So ordering of the variables is unimportant. That's the first thing, and that's important. A lot of students forget that. It doesn't matter which comes on the explanatory axis. Second, it's a unitless quantity. Why? Because we use z-scores to calculate. Z-scores are just a number of standard deviations. They have no units. So correlation coefficient will never have feet, yards, inches, etc., etc. Third thing, shifting and scaling does not affect the coefficient. Why? Well, whenever you shift the data, if you add, let's say we took all the student GPAs going back to the beginning of the notes, and we added 0.2 to all of them. Hopefully you remember from chapter, I can't remember if that was 5 or 6. In chapter 5 or in chapter 6, we talked about the fact that if you add the same number to a whole bunch of data, you're not changing the number of standard deviations that you are from the mean. Remember, all the measures of spread do not change when you shift. And guess what? The correlation coefficient is determined by measures of spread. It's determined by z-scores, number of standard deviations. So shifting has no effect. Scaling also has no effect because let's say you scale data by going from I weigh 207 pounds. If I take those 207 pounds and then scale by 16, multiply everything by 16 to get, well, let me back up. Let's say I've got everyone in a class and all their weights. Let's just look at now my individual weight. It's 207 in pounds. If I multiply by 16 to get the everyone's weights, including my own, in ounces, 16 ounces in a pound, that doesn't change how many standard deviations you are from the mean standard deviation weight for the class, or from the mean weight of the class, rather. It will change the standard deviation, but it won't change how far you are from that mean, or the number of standard deviations you are from the mean. So, and that goes back to the fact that number of standard deviations you are from the mean just doesn't change regarding the units you choose to use. So shifting and scaling both don't affect the correlation coefficient. That also trips people up. Watch out for that. 4, only the strength of the linear association is determined by the coefficient. Right, so if you've got data that's got some a quadratic look to it, you might have a very strong association in that data. And this data right here does seem to have rather a relatively strong association. But the correlation coefficient will not pick up that strong association because it assumes the association is linear. It's the only form that the correlation coefficient will work with, a linear form. So be careful in how you apply the correlation coefficient. All right, last thing here. If we have outliers, we should calculate the correlation coefficient with and without the outliers. That is to say, you should have 2 correlation coefficients, one that's outlier-free and one that includes them. Why? Let me show you really quick. Let's go back to this guy right here. Okay, in blue, we had looked at all these positive contributions to make a positive correlation coefficient here equal to 1. Well, check out what happens if I add just one negative point way over here. Clearly an outlier, a huge outlier in this case. Now we've got, remember, the correlation coefficient is determined by adding up all these standard deviation boxes. You've got all these positive boxes in blue. With outliers, they have a huge contribution to the correlation coefficient because they're far removed from the center of the data. Okay? It's basically, everything's determined by distance in some sense from where the mean of x and the mean of y are hitting, right here. Okay? So with this red point that I just added, you've got a negative z-score from the mean of x, and you've got a very positive z-score from the mean of y. Hence, when you multiply the negative and positive together, you get a huge negative contribution. That's going to have a nasty impact upon the correlation coefficient, and therefore you would not see a correlation coefficient even close to 1. With that single point, even despite the fact that you've got 7 points that are perfectly in a line, you get a correlation coefficient closer to like 0.5, all based upon the huge influence of that one red point. Okay? So these notes, much trickier than the first Chapter 7 notes. You guys have done a good job hanging with. Let me end it here. I'm sure I'll have questions on this stuff next time. I'll try to